Hi, everyone. Welcome. So I'm going to give a quick talk on time-weighted averages. I think we talked about we're going to do questions at the end. I think most of you know who I am, but we do have a few new hires or people who I haven't interacted with quite as much as we get a little bigger. I'm David Kohn. I've been here for over 3 years now. Been working in databases for over 5. But before that, I was an electrochemist. And so I saw a lot of these. This is basically a battery discharge curve. It's sort of an idealized one. On the x-axis, you have capacity, which is in amp hours. And if you are actually sort of thinking about this, is probably a constant current discharge. So the amps are constant. So it's really just a proxy for time on the x-axis. And you have cell voltage on the y-axis, which is really going to end up determining the power output during the discharge of the battery. And so this basically is showing you, as the battery keeps going and provides power to something, how long will it last? What can we do with it? So this was the common sort of curve that I would be looking at in the electrochemistry world. And really, the part that I want to highlight here is that there were sort of interesting bits at the beginning and end where the voltage changed a lot. And then there's a boring part in the middle. And in there, the voltage is basically constant. And so because a lot of stuff you could learn about the battery was during those interesting bits, right? So when we're cycling these batteries, we're trying to figure out for a given formulation. So we make a cell with some materials and we cycle it. And we want to try and figure out how long this is going to last. Now, there's some stuff you can learn from that middle part, but the data just isn't changing that much, so you can't learn that much. But at the beginning and end, the sort of relaxation of the cell as you start cycling it or towards the end, that can give you a lot of information. And so you want to sample much more quickly during those parts. So we take more data during the interesting parts. That was basically our solution to this problem. We have the interesting parts, we have the boring bits. The boring bits, by the way, this is over hours. So that whole cycle is over 10 or 12 hours. It's not a short thing. So when I said that I was an electrochemist earlier, I was exaggerating a little bit. I knew enough about electrochemistry to be dangerous, but I was working with folks who had PhDs and knew a lot more than me about batteries. I was sort of a potentiostat programmer and the data guy. That's what I fell into. I knew more about that stuff. So we program our potentiostat. That's a picture of a potentiostat. The potentiostat's the thing that you hook up the battery to in order to cycle it. Here it's connected to some, I don't know, this is biologic potentiostat connected to some half cell, basically. And so we would program the potentiostat to basically sample every 3 minutes, or when the voltage has changed by more than, say, 5 millivolts or something like that. And it could sample that way. So what we'd end up with is a curve that looks something like this. We'd have more data during those interesting bits. The data points would be closer together. And then during that long boring bit, we just have fewer samples. And then we'd have more again during that end part of the curve. So, and this was actually pretty common across industries. This is not just the thing that we see in batteries. We especially see it in industrial IoT, where they do something that they call compression, which is really just saying, whenever the data changes, send me a new point. So that's what they sort of call compression in industrial IoT. In other places where they want to avoid sending uninteresting data over the cell network. So in remote sensing, you'll take more data when there's something interesting going on, less data otherwise, because basically cell data, especially when you're in remote locations, can be very expensive to send back. So you can get significant savings by only sending more data when you have something really interesting to send. Sometimes there's data loss in the network, especially again in those sort of remote locations. And then there's other cases where we have event-based triggering of different sampling rates. That might be something like, say, a home security system, where you have sensors that are relatively low power. You want the battery to last for years. And so you only trigger such and such sensor to start really taking more data when a motion sensor triggers or when something else happens. Okay, so we've established that it's common, and we have this sort of differing sample rate regime here that we see. So here's the question that I want to ask. How do we get a representative average? Like, what's the average voltage during my discharge? So we have these data points, and we have more at the beginning and the end, but just because it's more interesting there, it doesn't mean the data should count more, right? We don't want our sampling rate to affect the outcome of that voltage measurement. And the voltage measurement, by the way, was important because it was one of the higher level things that we could measure about this whole discharge that then would tell us as we cycled it more times, 10 or 20 or 100 times, okay, we can look at say the slope of the voltage, and it's going to be decreasing. And that's going to tell us something about how the battery is aging and how many cycles we're likely to get. But if my sample rate changes, then I can't really compare it if I don't take actually a representative average. I don't want the sample rate to just wash out all of the interesting stuff that I'm trying to find in the actual data. So the basic question that we're trying to answer here with a time-weighted average is how we get a representative average when we have irregularly spaced data. So I'm going to go into a little bit of theory now, and then we'll get into some more stuff, like examples of how to do this in SQL in a bit. So the theory behind this. So let's consider basically this sort of simplified version of a time series with irregularly spaced points. We have a few points on this graph. The normal average, right, would just be this: v1 plus v2 plus v3 plus v4, add up all the values, divide by the number of values. Okay, that's our average. But if I want to get this sort of time-weighted average, what I can think about doing is basically taking, in essence, almost the integral. So it's something where I'm taking the area under the curve, or the value at every time, or as close an approximation as I can get to that, and adding all of that up and dividing by the total duration that the process happened. So that's basically what we're going to try and do in a time-weighted average. We're going to add up our best guess of what the value is at every point in time and then divide by the total time. And that's how we're going to get this better, more representative average for irregularly spaced points. So that's eventually going to be the area under the curve divided by that full time period delta t. So let's look at then, when I'm doing this in the real world, I need to look at basically the data that I have, which are these points. So I need to take basically the area between 2 points, figure out the formula for that, and then I can just add all of that up between each point and then divide by that larger delta t at the end. So looking at this sort of trapezoid here, we can actually see that it breaks down into just a rectangle and a triangle. And if I look at how I would get a formula for the area of that, it's going to be something like this, where I get the area of the rectangle and then the area of the triangle. I'm going to add those up. So between T1, V1, T2, V2, my first 2 points, this is going to be the area that I get for that part. So I'm not going to go through all of the simplification steps, but I can, in fact, simplify this to think about it in a slightly different way. It's actually the average of V1 and V2 multiplied by the time, which in a graphical intuition is also the area of the rectangle drawn to the midpoint between the two values. And so the area of that trapezoid and the area of this rectangle are equivalent, which I like. So that ends up being the basic formula for what we're going to do between each point. Cool. So that's nice. Let's figure out how to do this in SQL. We're going to consider an ice cream business because we want a simplified case. And in an ice cream business, they have freezers. They're storing their ice cream in the freezer. And people open the freezer doors. And what we want to figure out is if the ice cream is going to freeze and thaw too much, because if it freezes and thaws too many times, then it develops those grainy crystals. It sort of tastes sandy. No one likes that. We also can't get it too low in terms of temperature because then, you know, it will just be impossible to scoop. So here we are in the ice cream business, and we're going to talk about this sort of variable sample rate based on a trigger in this case. So we start in steady state, we're at 5 degrees Fahrenheit. Someone opens the door, the temperature spikes up to 30 degrees Fahrenheit. And so we start sampling at every 5 minutes when we're at that normal sort of steady state operation. When the door opens, we start sampling at 30 seconds. And then eventually our sample rate is going to go back down to every 5 minutes once we get back into our targeted range of temperatures, maybe at 15 or 10 or whatever it is that our target range is going to be. And to model this in SQL, we're going to have a table something like this. Pretty simple. We have freezer temps, we have a freezer ID, we have a timestamp, and we have a temperature. Okay, so how do we write this time-weighted average that we just derived in pure SQL? So with normal SQL, we're going to have to do something pretty complex. We're going to use a couple window functions to basically try to get the overall time period as well as the previous temperature at each point. We're going to take the average of them. That's what we're doing over here in next step. And then we're going to divide by so we get a lot of steps in this. You can go through and try to understand it, but that's okay. Because this is exactly what we on the toolkit team have been working on hyperfunctions for. Because that's just a bit long-winded and yeah, just really not great. So hyperfunctions are functions that are made to solve these sorts of complex problems that should be easier. So this is how we implemented it. We have an aggregate that's going to do all of that weighting for us. It's going to produce basically the weighted sum, which is basically equivalent to the area under the curve. And then we're going to take an average of it. And the weighting here is linear. That's because we're basically doing linear interpolation between the points. That's what we did. That's why we got that triangle or trapezoid rather than a square. So this is what it's going to look like in a hyperfunction. It's much simpler. And a lot of the reason for that is if I want to then build up more complex analyses on top of that, if I start with something like this, it becomes just a code maintenance nightmare, right? The person who comes along behind me and is trying to figure out what the heck is going on when I've written out this large thing, unless I've really documented it nicely, they're not going to know what to change in order to then go and do something more, build something more complex on top. So a lot of what we're trying to do with hyperfunctions is take things that should be fundamental to time series analysis and make them much simpler to do so that then our users can go and take them and build them up into the complex business logic that they need in order to get the real insights into their data. So it makes it much more composable. So let's, like if I wanted to do a time bucket here, I just simply add a time bucket. Easy. And it's something that is very obvious to the user that that's how it's going to work. Or in this case, I might want to work in a window function because I want to figure out the rolling time-weighted average because I need to know if there was any 15-minute period where the average temperature exceeded some value, because then I'll know that it might have crystallized. So I can do that very easily. I create my window where I'm partitioning by freezer ID and I'm ordering by timestamp, and I'm going 15 minutes in the past. And then I know at every point what the 15-minute time-weighted average of the temperature was in my freezer. So that's going to really tell us something much more nicely about how we can do this stuff. It allows us to build up really nice analyses, and that's the basic gist of time-weighted averages. And that's it. That's the presentation. So I'll ask for questions and see if there's anyone who has anything. I guess I can either stop sharing or I might want to refer to slides. So maybe I'll keep sharing for now. Miranda?
Yeah, I just have a quick question. So I saw in the examples that you used, we're using linear for the interpolation method. Are there other interpolation methods that we could use?
Yeah, so there are. Thanks. Yeah, so as we saw here, so this is the interpolation method that she's talking about. So in this time weight function, we're using a linear interpolation method. There is another interpolation method. It's called LOCF, which stands for last observation carried forward. So just to give you an idea of what that looks like, I actually have a couple slides on this. So basically there, we're just taking the previous value and assuming that it continues until the next value. So this is useful for something where you have some sort of system that provides a guarantee around that. So when we talked about that industrial IoT case where they do compression, where they basically just say, we're only going to send points when they change, that's when you use LOCF weighting. If you just have varying sample rates, that's when you use the linear weighting. And you can see the difference here that, that we're sort of just doing a linear interpolation between 2 points in the linear weighting, whereas with LOCF, we're carrying that previous value forward and just making sure that that stays for the whole time. Cool. Any more questions? And that got moved down, but.
I've got a question, David.
Yeah.
So in your example, in your usage example, and sort of this whole thing is talking about averaging time weight, but by the syntax, it looks like time weight is the function and is being wrapped by the regular SQL average aggregate.
Yeah.
Are there other aggregates you could use here?
So average, actually, this is not the regular SQL average. This is, so the regular SQL average is actually AVG.
Oh, right.
But it's, so it's slightly different. We just wanted the syntax to work nicely. Time weight is made this way because we wanted you to be able to roll it up. So I don't actually have an example of this in this presentation, but we're going to be releasing a blog post tomorrow where we'll have some more examples of this, and then I'll be going into it even more in some future things, I think, around continuous aggregates. But a lot of this is made to work with continuous aggregates. So the thing about time weight is it does produce a more complex data type. It doesn't produce the average directly. It produces basically an intermediate form. So the time weight here is basically the aggregate, and it's going to basically have the first and last values plus some weighted sum, as well as, depending on the representation, it might tell you which representation it is. Or which weighting method, I should say. So that then can be combined as long as it's ordered with other time weights. So if I have, say, a continuous aggregate that's doing this every 15 minutes, every hour, and I want to then get a daily weighted average, I can do that. I just use the roll-up function on the time weight, and then I use average to get the average out. So basically, average is just saying, give me the average out of this time weight. And this is a common device that we're using in hyperfunctions. You'll see also in like our percentile aggregation, we have a percentile ag function, and then you can extract an approximate percentile. You can have, and you can also extract something like the error, or you can extract the like percentile rank, which is saying, if I give you this value, what percentile would it be in? And we may eventually add in more functions to percentile or time weight, where you can extract different values from them. But it maintains this ability to roll up at different levels. So you can keep doing that roll up. You can even do tumbling windows in some cases where you would do a rolling type of modifier on that. John?
Yeah, in your examples, the first and last data point line up with the time window that you're averaging. Does it handle the cases where they don't line up perfectly, or do you have to do something extra?
So we do not currently handle that. That's something that we're probably going to add in at some point in the future. You actually need some sort of windowing function. We're probably going to add something like a look back, essentially, so that you can actually go to the edges of the range, a look back or a look ahead. We haven't completely come up with the naming for that. For right now, it's just going to work if your values are within the range. But it will also work if you do that roll up to get things that are outside of it. So you can at least combine multiple ranges together. But right now, the windowing part doesn't quite work that way. So you can't look outside of the range yet. Anything else?
Yeah, I was just going to add on. I think that, you in answering Tyler's question, I guess just to maybe clarify or see if you need to clarify any, you know, your example here is average. We have rollup is the only other one that you can use with time weight, right? So it's another, it is another way of taking a time weight and getting some additional value out of it. I know there's some samples and documentation for that. And as you said, it's really all the other things we're creating so far, like percentile approximation, which we'll talk about in a couple of weeks. It's the same thing, right? So we're trying to create, and the real value, which you said, I just want to like, because it was the big point for me, that was the aha moment, right? Like, oh, I can now make a continuous aggregate, store these representations of my data so that 6 months from now, if I need to come up with a different rolling, you know, period time bucket or whatever, all of a sudden I can do that, which is something we can't do currently. Continuous aggregates.
Yeah, that's the basic gist, is we are trying to make this work really nicely and play nicely with continuous aggregates and other sorts of more advanced features of the product.
And then I'll ask just one other thing for you to explain, and I'll probably ask every time we talk, just to get this out there. We introduced with the toolkit, and we're going to be doing this soon, probably in TimescaleDB as well, but the idea of this experimental thing. So these were originally released back in January as experimental functions that people could install and play with. And now we've said, hey, these are A-okay. We're not going to support these moving forward. And so what are some other examples, you know, that might be coming up for anyone who catches this video or anything else in the next few weeks?
Absolutely. So, so we have a few other experimental functions that you should definitely check out. So we have some really nice stuff around downsampling for graphing. LTTB or ASAP smoothing. We also have counter aggregates. So similar to this, where people have things that are supposed to be monotonically increasing counters, but they actually have resets. We have aggregates that take that into account, so you don't have to write horrible window functions to deal with them, and they play nicely with continuous aggregates and actually take on some of the sorts of ways that Prometheus, for instance, can work with counters. We also have some stats aggregates, which are just re-implementations of the basic statistical aggregates that say Postgres provides, but in this sort of format where we have rollups, where we have rolling. So you can do, they're meant to enable things like rolling averages, which right now are very difficult to write, like surprisingly difficult to write in SQL. But that makes it a much easier syntax for that. So those are the types of things that we're developing. I'm probably forgetting some stuff. I think we have hyperlog coming, other sorts of fun functionality. So that's some of looking down the pike. And yeah, we definitely love for you to go in and try out the toolkit experimental schema and mess around with those functions. Matt.
Yeah, I was thinking what you could do with this time weighted thing. And besides average, do you have any capability of getting things like the sampling rate out, or figuring out the average sampling rate across all of your, you mentioned the sampling rate regular, but you should be able to get some kind of statistical information, including average of the rate, variance of the rate, stuff like that.
That's interesting. Yeah, I think that's an interesting thing. I'm not sure that I would necessarily do it inside the time weight functionality, but it's certainly something that we can think about doing inside, say, the stats ag, like a single dimensional stats aggregate over a time. So we just need to make some functions basically for casting times to and from something that the stats ag can understand, which we do in some cases already. So I think that's a really interesting thing to do, and I think that would be a really interesting way to go about that. So we'll have to think about that. If you want to open an issue on our GitHub, that would be lovely, or start a discussion around it. That's how we take these things.
David, I was also just going to say, I don't know if you can reshare your screen. It might be worth just quickly clicking on docs so people see where documentation of these functions, and we're adding more information about them that way.
Sure. And I think Gayatri had a question though before we do that.
Oh, go for it, Gayatri.
Right. I was going to ask you, how exactly would you use time weight with continuous aggregates? I mean, the example asses wouldn't work because of the window function.
Yeah. So time weight will work with continuous aggregates, you'd probably do something more like the time bucketed one. In this case, so you just remove the average call here and just use the time weight. And then that's what goes into your continuous aggregate, just the time weight call. And then you'd apply average sort of in the query when you get things out of the continuous aggregate. So you basically say time weight, then you can roll things up. You can do whatever else you want. So if you wanted to get an hour out of your 10 minute, out of your 10-minute bucketed window or bucketed continuous aggregate, then you just run roll up on it and then get the average out. So basically you just run that first part of the aggregate inside the continuous aggregate definition, or that's what we'd recommend. But we'll also be doing some more sort of stuff around this as we continue. Let me see if I can get to docs quickly. Docs.TimescaleDB. So if you want to find some of the stuff around this, you can go to the API reference under hyperfunctions. You'll see our percentile approximation and time-weighted averages are the ones that we just recently released. Those are the ones that are stable. And then if you go to the TimescaleDB toolkit, let's see. You can go to the docs page on GitHub, and that'll give you some of the other stuff like counterag docs and all the stuff that's in experimental. It'll give you docs for that sort of thing. And so these are the accessor functions that we were talking about, and then the aggregate functions, et cetera, as we were talking about there. So that's all.
Awesome. Dave, thanks so much. That was super helpful.
Thank you guys for joining.